Okay, Assalamualaikum and good afternoon kepada semua. Kita akan adakan seminar Jabatan Fizik once again. So, speaker pertama daripada siri ini adalah Dr. Nur Adilah. So, sebelum kita mula, saya perkenal sikit daripada CV beliau. Okay, beliau mendapat pendidikan bachelor daripada Universiti Melaya 2010 dan University of Sheffield untuk masters dan PhD Universiti Melaya pada tahun last year. Okay. So beliau juga ada pengalaman dengan industri Sony dengan Infineon Technologies. Okay. Dan beliau sangat aktif. Antaranya adalah I think apa tu Film Lab pada tahun 2019. So, beliau akan menyampaikan presentation hari ini, seminar hari ini bertajuk Vanadyl Tetrabutyltetrakis Dimethylamino Phthalocyanine based thin films for organic sensor and transistor applications. So saya harap saya sebut betul.
Betul.
Okay, silakan.
Alright, okay. Boleh nampak saya? Okay. So, Bismillahirrahmanirrahim. Assalamualaikum and good afternoon to fellow lecturers, and I think we have one student here. Okay, so Assalamualaikum and good afternoon to fellow lecturers and my dear students. So before that, I want to say thank you to Dr. Hishamuddin for inviting me for this seminar, and thank you to all lecturers for spending your precious time to come to join for this meeting. Okay, so I think I don't need to introduce myself because I did prepare to introduce myself, but then I don't think I need because I think most of the lecturers knows me. So I will just proceed. So basically, this project, this presentation is what I did during my PhD degree. So the title of the project is Characterizations of Vanadyl Tetrabutyltetrakis Dimethylamino or VTP, thin film for organic sensors and transistors. But don't be afraid to see the name because you know the polymer and also the polymer and the organic, the small molecule, the name is usually quite long, right? So here. This is the outline throughout my presentation. So first I will introduce a little bit on the organic semiconductor material, and then we will see what motivates me and the objective of this project, and we will see what is the methodology, and then we will go to see the most important part in this presentation, that is result and discussion, and finally I will wrap up the presentation. Okay, so first of all, when I talk about organic semiconductor material, okay, this is a true story. Whenever I talk about organic material to people, people might think that I extract the material from the plant or the fruits. Okay, because it is organic, right? So people might tend to think that I extract the material from the plants or fruits to fabricate my device, but actually it is not. I think you know already about the silicon. So silicon, the molecular structure of the silicon, there is no carbon, there is no hydrogen. So that is why the name of the silicon is non-carbon based material. But the definition of the organic semiconductor material, it is defined as the carbon based material. Okay, so basically in the organic semiconductor material, it consists of the carbon and also the hydrogen. The bonding lah, the carbon and hydrogen bonding. Okay, so in terms of the price, obviously the organic material is way cheaper compared to the inorganic silicon. That is why you can see that in the market right now, in the industry and also the researchers are right now they are tend to substitute the conventional usage of the inorganic silicon with the organic material. Like right now we can see in the market we have the OLED TV, right? So the OLED TV is the comes from the organic light emitting diode. So that means it used the organic material as a display. Okay, let me, sorry. Okay, so let me go further to the aspect on the organic semiconductor material. So it has few important aspects. For example, the first one in terms of the bonding interaction. So in inorganic semiconductor material, the bonding interaction between the molecule is pulled by weak van der Waals forces. Okay, it is a weak bonding. So due to this weak bonding, the conduction mechanism is by using the hopping mechanism here. The hopping mechanism, because you know that the molecular orbital energy splitting that contributes to the molecular orbital. So it is by the conduction mechanism is by using hopping mechanism. And also you must know also the valence band. Usually we learn about the electronics, we know the term valence and also the conduction band, right? That make up the energy level. So we have the valence band. It terms as the HOMO in the organic semiconductor material, and the conduction band is termed as the LUMO. So HOMO stands for highest occupied molecular orbital and LUMO stands for lowest unoccupied molecular orbital. And also the properties of the organic material that you have to know is it is amorphous material. So I think most of us know about the solid state. So because of the amorphous material, it presents a lot of multiple traps and defects, and due to these traps and defects, it contributes to the low carrier mobility here. And the most important part, the most interesting part in the organic semiconductor material is in terms of the production method, in which it is a low cost in terms of its material and it is easy in terms of the fabrication process. So what I mean by easy fabrication process here is we can just use the solution process method. So there are few advantages of the solution process method. I think most of us know. First is the simple fabrication process, in which we can just dissolve the powder with the solvent and then we can just do the spin coating method, and then it is a low cost in terms of its material and then processing, and then it can produce in a large scale production. Okay, so under organic semiconductor material, we can classify that material in two. One is polymer. So the example of polymer is P3HT. The example, and the other one is small molecule material. So the example of small molecule is PCBM and also the MPC. So the MPC is metal phthalocyanine. So this is what I will focus in this project, the MPC, the metal phthalocyanine. So what is the interesting part of the MPC that I really want to study? So you can see this is the molecular structure of the metal phthalocyanine. So you can see here at the central cavity, it consists of the metal atom. So basically the metal atom here, this is what that makes up the name of the molecular structure. So for example, we use the copper atom. The name of the material will be copper phthalocyanine. So if we use the zinc, it will obviously the zinc phthalocyanine. And okay, so the properties that consist of the exhibits by the metal phthalocyanine is first, it is a thermal, it has a thermal and chemical stable. So what I mean by thermal and chemical stable is the material or the powder, for example, the powder, because we don't synthesize this material, we are not a chemist, so we just use this material to study the organic device. So if we have the powder of that material, we can do the evaporation technique. So you know that the evaporation technique is we need a very high temperature, right? So it can be sublimed without any decomposition. So compared to the without any decomposition, right? So the second properties is it is a versatile material in terms of the chemical flexibility. So what I mean by versatile is, as I mentioned just now, this central cavity can be substituted into more than 70 central metal. So for example, if we use other metal, so each one of them will give different properties to the different properties to the device, okay? And then the extension of the pi system can tailor the physical, electronic, and also the optical properties, as well as to improve the solubility. So the extension pi system here is the ligands at the molecular structure. So after this, we can see what is the extension pi system. And then it can be used as the display, for example, the one that I mentioned just now, the OLED, and then the OFFET, transistor, sensors. Okay, there are a lot of applications that can be used by using this small molecule material. Okay, this project is divided into 3 projects. One, am I too fast? No, right? Okay, so so this project is divided into 3 parts. One is transistor, photodetector, and humidity sensor. So basically, this is the main material that I will be I studied. The name, as I mentioned just now, the central cavity will make up the name of that material, right? So this is the central cavity. Here is the vanadyl or the vanadium. So the name, that is why the name of the material is Vanadyl tetrabutyl. Just Tetrabutyltetrakis, so it depends on the ligands here. So, okay. So it depends on the ligands here. You know chemists, right? So they tend to like name the molecular structure like one by one. So that is why the name of that molecular structure is quite long. Okay. So basically, I will. Where is my cursor? Okay. So basically, this material I will study as an active layer in this application or in this device, transistor, photodetector, humidity sensor. Okay, so now we have to see, now we want to see what are the review of the development of metal phthalocyanine in organic devices. All right, so you can see that I focus on the VOPC here. And on 2015, there is one work that has to be reported on the properties of VTP-based nanostructure. And he claimed that the photophysical properties of the VTP shows a good properties in to exhibit in optoelectronic devices. So this is going to be my research gap, in which there is no works has been reported regarding the other properties of VTP and VTP-based organic devices. All right. Okay, so why I use PCBM here? Because I want to fabricate, because for my project too, I want to fabricate a bulk heterojunction photodetector, and it matches well with the energy level alignment of the VTP. And why I use VTP here? Because it has high solubility, and also obviously we want a low cost material, so it is a low cost organic material. All right, so this is the molecular structure of the VTP and also VOPC. All right, so this is why I just focus on the VOPC development organic devices. So you can see that the molecular structure of the VOPC and VTP at the central molecular structure is quite the same. The only difference is in terms of the ligands here. So VTP consists extended ligands at the sites here, which contribute to which affects the properties of that material. So this motivates us to proceed with the project. So comes with the motivation. So this is the motivations of this work. The first one is the extended ligand in the molecular structure of the VTP. The extended ligand, this extended ligand, the one that I just mentioned just now. So it possesses relatively high charge carrier mobility, but within the MPC group itself. And then highly conjugated pi system is good for photosensitivity. So you can see that between the VOPC and VTP, VTP consists highly conjugated pi system, and then hydrophilic properties of the VTP. So this is for the humidity sensor, because for the humidity sensor, we want the hydrophilic properties. It must like water. It cannot like this like water. So come to the objective from the motivations just now. I have 2 big objectives. That the first one is to characterize and study the physical properties of VTP, which include the optical, structural, and also the electrical properties. And then I want to fabricate and explore the VTP-based devices in transistor, photodetector, as well as the humidity sensor. Okay, now we sorry. Okay. Now you go for the methodology part. For the first project, that is VTP-based organic field effect transistor. So you can see, So because my objective, because I want to differentiate the performance of different architecture of VTP-based transistor, right? So I have to fabricate 2 architecture here. One is lateral offset, the other one is vertical offset. So you can see here, this is the fabrication of the lateral offset. Basically, this is like the conventional offset that we already seen in the transistor. That is, I use the ITO and then I spin coat the PVDF therapy as my dielectric, and then this is the main objective, that is VTP as the active layer, and then I evaporate the metal, that is aluminium, as my drain and source. As for the vertical offset or VORFET, in short, all the parameters are same, but the only different is the silver nanowire that acting as the source electrode. Because theoretically, in the fabrication of the VORFET, you must know that the middle electrode or the intermediate electrode, it must has the thin and rough morphology. So that is why I choose silver nanowire as my source electrode. And also, okay, so you might wonder why I fabricate different architecture. It is because I want to modify the channel length of the device. Okay, what is the definition of the channel length? The channel length actually is the one that contribute to the conduction of the device. So for example, the channel length is defined as the distance between the drain and also the source electrode. So you can see here in the lateral offset, the channel length is defined within these two distance. But for the vertical offset, the channel length is defined by using a thickness of the VTP layer. Alright, so the thickness is going to be your channel length. Okay, now this is the photo for the silver nanowire because I want to confirm it is a rough morphology. So yeah, I did the FM and it shows that it is a rough morphology because I have the RMS value for sure, obviously. And then we go for the second project for the optical device. So this is how the architecture looks like. So I use the ITO glass substrate and then I spin coat the PSS and then I mix the VTP as the P-type and also the PCBM because I want to fabricate a bulk heterojunction device, right? So I have to mix these two materials together. And then I spin coat on top of the PSS and finally I will evaporate the aluminium. And this is the energy level alignment of that device. So you have the ITO, PSS with the energy band gap. So this is what I call by hopping mechanism, in which your hole and your electron is transported to the respective electrode by using a hopping mechanism. Okay, so next for the third project is humidity sensor. So the fabrication of the humidity sensor device is very simple. So you just use the glass substrate and then you you evaporate the aluminium and then finally you spin coat the material. And this is how the setup of the humidity sensor. This is the chamber here is just the homemade chamber, but it works. Okay, so the nitrogen gas is to dry out the vapor. The humidifier is to supply the water vapor. Thermohygrometer is to check the RH value, the relative humidity value inside the chamber, and the LCR meter will give the performance of the device. And this is the final device that we fabricate. Okay, so for the characterizations, I divided my characterizations into 4 parts, that is optical, morphological, electrical, and finally I want to test for the device performance for every device. Okay, now we go to the results and discussion. You must know, before you fabricate any electronic device, you have to know the properties of your material. Like in my case, I have to know what is the value because it hasn't been like reported previously. So I have to determine the value of HOMO and LUMO and also the band gap of that material. So the value of HOMO and LUMO is determined by using the cyclic voltammetry, and you can see this is the oxidation peak and this is the reduction peak. So I take the value of the onset value here and I plug into this equation to get my HOMO value. This is the same method, so I take the onset value, plug into this equation to get the LUMO value. So actually there is one other method to study for the HOMO and LUMO, that is by using the UPS. UPS ultraviolet photoelectron spectroscopy. So by using the UPS, it is more precise compared to the HOMO and LUMO, compared to the cyclic voltammetry. So to calculate the energy band gap, I use the absorption spectrum, and this is the absorption spectrum of the VTP looks like. Alright, so I use this equation to calculate the band gap, and I take the onset value, or I extrapolate from the highest peak here, and I plug into this equation, and I get the value of energy band gap as 1.4 electron volt. So actually for the energy band gap, you can also determine by using the top plot. I did measure by using the top plot, and we got the same value, like by plus minus 0.01 like that. Okay, but at least it around that number. So the value from this equation and the top plot, I got the same. Okay, so after I determine the value HOMO and LUMO and also the band gap, I can fabricate the device. So first I fabricate the lateral offset, which acted as my control devices. So you can see, if you know about the transistor, you must know that the normal characteristic that the transistor have is the output and also the transfer characteristic. So for the output characteristic, for the low FET here, you can see it is only linear region, and it is unable to achieve the saturation region. This is because most of the offset will acting or can behave at the higher voltage. But right here, we just apply until 30 voltage. So usually for the offset to work, it needs like high voltage to get the saturation region. So we think that maybe by reducing the channel, maybe we can reduce the threshold voltage. Okay. So for the transfer characteristic, I got two curves here. For the red line is the cert ID versus the VGS, and also for the black line is ID versus VGS. So for the cert ID versus VGS, you can get the value for the threshold voltage, in which you can just extrapolate the value to this x-axis, okay, and then you can get the value for your threshold voltage. And for the turn on-off ratio, you can divide the value for your maximum ID by your pinch of current to get your turn on-off ratio. Okay, just now I mentioned to you that the in VOFET, the thickness of the active layer will define my channel length. So what did I do is I have to optimize the thickness first in order for me to see which thickness or which thickness is the most suitable one for the fabrication of the VOFET. So I varied like 4 thicknesses here from 500 until 3000. And you can see that it is able to achieve the saturation region. But okay, I will summarize this parameter in this table. Okay, now we focus on the vertical arrangement first with the variation in the spin speed. Okay, so you can see that at 2000 RPM or around 70 nanometer, my device works better compared to the rest of the thin film. It is suggested that the thickness or the spin speed or that give the thickness will dictate the supply volume of the charge carrier. And then we focus on the arrangement here, that is lateral and the vertical. So you can see for the lateral and vertical with the same RPM speed for 2000 RPM. Okay, so you can see that for the vertical offset, the performance is much better compared to the lateral offset. So we can deduce here that by reducing the channel length, it will improve your hole injection or your conduction mechanism from the source electrode to the top electrode. So that is why it can give the much better output current compared to the lateral offset. Alright, so for the second project, that is VTP-based optical device, we have to characterize first, in which here I characterize by using I want to study the optical study and also the morphology study. So for the optical study, I did use for the UV-vis and also the PL. So you can see here for the VTP, the red line is VTP. It only absorbs certain range between 300 to 400 and also 700 to 900. it is unable to absorb around the visible range. But for the PCBM, it can be absorbed from 300 until 700. So why not we combine these two material together, right? So we can get, when we combine these two material together, we can get this type of absorption. And then we try to vary the PCBM content. And then it suggested, it is obviously shown here that 1:4 ratio has the best absorbance compared to the rest of the thin film. Now we characterize by using the PL spectra, and the PL spectra shows that 1:4 ratio has the best quenching effect compared to the rest of thin film. So in optical study, I think that 1:4 ratio has the best film compared to the rest of thin film, but then I need to confirm with the AFM. Okay, the theory for the AFM here is we need a rougher surface compared to the smoother surface, because a rougher surface is needed because we want to improve the contact between the active layer and also the electrode. So that is why we need more rougher surface compared, okay, we need rougher surface. Okay, so the theory in RMS is the more higher your RMS value is, the rougher your surface thin film. So here, 1:4 ratio has the best RMS value, so that is why we proceed with 1:4 ratio to fabricate our device. So these are the electrical characterization of the photodetector. Sorry. So you can see here, as I varied the light intensity, so this is the variation in the light intensity from the dark until 90 milliwatt per centimeter square. So I increased the light intensity. So you can see the response of the photocurrent density is improving. Okay, and then I did calculate for the ratio of photo to dark current, and it get like a quite good number in the ratio. And the theory behind this is we have to have like a good a large number of the ratio, because it will improve the noise rejection ability. So this number is quite good. This ratio is quite good. If we compare within the small molecule material. And then here, the second figure here is as I varied the voltage, it is also responsive. I mean, the photocurrent density is improving. And here is the time response and recovery, in which I switch on and switch off the light, and then it shows a stable output and repetitive output with the rising time in 350 millisecond and the fall time with the 40 milliseconds. So the output is quite fast, and it is a stable output. Okay, so by now we think that, okay, so it can like works better in, it can works in the photodetector device. So we try to use the same device, and then we just adjust the characterization setup to measure the solar cell performance. But unfortunately, the PCE or the efficiency is not that good for the solar cell. It is like below 1%. So it is not good for solar cell. So that means this material is not work for the solar cell. So this might be attributed to the lower absorption spectrum. So the absorption spectrum within the visible range is not enough to convert from the light energy to the electrical energy. Okay, so this is the characterizations for the humidity sensor, in which I divided into three. For the capacitive response, to calculate the sensitivity, hysteresis, and response and recovery, and it shows that the thinnest film, okay, here I varied the thickness, and it shows that the thinnest film shows the most sensitive response compared to the rest of the thin film. Okay, so finally we go. We'll wrap up for this presentation. The properties of VTP has been studied and characterized in terms of its homolumo, energy band gap, and also the optical properties. The performance of the lateral offset has been improved by altering or adjusting its architecture to the vertical offset. And then the VTP-based optoelectronic devices have been fabricated. The stable and repetitive output of the organic photodetector has been achieved. And finally, the thickness of the sensing film plays important role in determining the sensitivity of organic humidity sensors. So these are my publications throughout my 3.5 years of work. Okay, and then this is the paper presented in the conference. And yeah, these are some activities that I did during 3 years of work, in which I did join for the competition. And this is the selfie with the chief editor of organic electronics, because during my first semester, I did like put my wish list to get published in organic electronics, and alhamdulillah, right now I managed to publish in organic electronics. It is the impact factor is not like okay lah, Q1. Okay, so this is with the chief editor of the organic electronics, and this is when I joined the FAME lab, and then this is when I joined the 3-minute thesis, and this photo is when I submit my thesis, and this is when I got selected for the Canada ASEAN scholarship, and this is where this is in Canada with the group. This is my supervisor, and this is my supervisor in Malaysia. And then after I went back to Canada, I went to Venice for my research training as well. But then it is not like long, it is like 2 months. 2 months because the Malaysian have to repatriate back to Malaysia because of the COVID. And these are just some photos during my travel. Okay, so what I want to highlight here for my dear postgraduate students, if they have here, so if you are a postgraduate student, please do not just sit in your lab and then mind your own business. Okay, you have to go out, meet people, and then build your CV. That is for your networking. And obviously, this is my photo when I got the doctor's title. So I think that is from me today. Thank you for your kind attention. If you have any question, you can ask me.
Thank you, Dr. Adilah. Let's have some Q&A from the colleagues, students. Otherwise, I have to make up. Okay, please unmute yourself. Who was that? So any question from colleagues or students? Okay, maybe I'll start off something very general because I'm not in this area. So you mentioned something about the VTP thing was not really studied before. Is there any particular reason for that?
Okay. How to answer this question? I'm not really sure about this because I tried to search in the from the paper, and it is not widely studied for the device. They just studied for the synthesize only. So they are more focused on the synthesizing the material. I'm not sure, me myself, I'm not sure why they didn't try for the device. So yeah, I don't have the answer for that.
Okay, okay. Any questions from the rest, please? Okay. Make it interactive.
I don't think we have a student here.
Your students left?
There is one.
Colleagues? Any question, I think? So you spent, you had Erasmus.
Yeah, I done Erasmus for my school, for the research training to Italy.
And
sorry?
And then it was cut short, is it?
Yeah. Because of the COVID, so I just, I was there for 2 months only, but we didn't get a chance to, we visit the lab, but we didn't get a chance to do the experiment.
What was the planned experiment?
About the rare earth metal for the solar cells. Yeah, focus on the solar cells. Yeah, but in the Canada, I did like publish with them for the transistor applications. So Alhamdulillah, we managed to get a publish for one paper.
Okay, please ask any more questions from the rest, not only from me. Only ask Jabatan, congratulations from Dr. Farah.
Thank you.
Anyone else? General questions? No. I can ask a technical question, but no, it may sound dumb. For instance, you mentioned about the surface has to be rough in order to get better performance. Usually it's the other way around. Or I'm not quite sure. That's a bit counterintuitive to me.
Because I read from the paper, we want contact between the active layer and the electrode, because we fabricate the device by using a layer by layer arrangement. So the contact must be there, so it can give like if we have like a smoother surface, the contact will not be there. So the contact between the active layer and the top electrode, I mean, for the solar cell. So it is layer by layer, right? So yeah, we need a higher the RMS value must be like not very rough, but then it is need to be optimized.
Okay, so some balance thing. Okay, colleagues, more questions?
All right, let me ask a question. Sorry, I joined quite.
Okay, go ahead.
What is the advantage of using organic instead of inorganic?
Oh, okay. So one of the advantage is obviously it is in terms of the price, the organic is much cheaper compared to the silicon. And then in terms of the mechanical, it can be flexible. So that means we can make a flexible device, because right now we are focused on the flexible device, right? For us to like attach on the skin or something like that. So we want that thing to get a flexible and then it can be bent if we stick on the skin. And also that is one thing that, second, first is price, second is in terms of the mechanical, and then for the silicon it is rigid. We cannot like do a flexible with the silicon. And then we can do the in terms of the solution process, in which it is a low cost processing techniques. And I think there are a lot actually, but then that is the only point that came up to my mind right now.
All right. So when you say it's organic, is mainly refer to the substrate?
Sorry?
Is it refer to the substrate? When we say that it's organic, is it just refer to the substrate?
It is referred to the active material that we use.
Oh, all right. Okay. Yeah.
Okay. Any more questions? I think we have quite long time to go to 4 p.m. 4 p.m. is my limit. Okay. Any questions from the rest, please? Film lab. Okay, maybe I ask first. Film lab. So on what device are you?
I focus on the solar cell, because
solar cells. Okay.
Yeah, that is the most easiest story that I can make.
Okay.
Yeah, I'm not a good presenter, I'm not a good speaker, but then I want to try and I want to challenge myself. So that is why I joined the Fem Lab.
But
Sorry?
you did say that the case for the solar cell, the efficiency is a bit low, right? So in between all these three devices that you have done, which one seems to be more better for performing?
I can say it is the best device for this material is the organic photodetector, because when I compare the performance with the other papers that have been published, but within the material itself, okay, within the small molecule materials, it is quite, the performance is quite the best compared to the rest of the paper that has been reported. Yeah. But for the transistor, it is not the case. It is just, I can say that this is just like a preliminary studies for every chapter. I mean for every device. So we want to see how is the performance and how this material behave if we use for every applications.
There is a question from Dr. Azura. Let me just read it. Any idea on solar cell application of RNA or DNA based?
I have to think about that. But then there is one paper that has been reported, but that this paper is not about the solar cell. They use the DNA for the application in the diode. But I cannot remember because that was a long time ago I read it. But there is one paper that used the DNA in the application of the diode. I think yes, diode. So they studied the performance of the diode parameter by using the DNA as the active layer. But to expand my explanation, I cannot expand more because that is the basic idea that I have for that paper. I read that paper like long time ago during my PhD.
Okay. More questions, please. Otherwise, we have to stop earlier. Maybe I should ask. I like interaction. So probably this is a question with respect to the department in a sense. I don't think there's anyone working on organic semiconductor in the department, right?
I think yes, Dr. Tansiti. Yeah, Dr. Tansiti is working on the organic semiconductor material.
So
Dr. Josephine.
So you have a group.
Yeah, I joined Dr. Tansiti and also Dr. Josephine.
Okay.
Yeah. So for my FYP, I need help from Dr. Tansiti. Yeah.
You're continuing with this organic semiconductor.
Yes, probably. But if I want to, for the start, if I want to continue this solar cell and also the photodetector, I have to collaborate with the UM because I need a glove box. Yeah, and for my FYP right now, I try to expand my expertise to gas sensor. Yeah, I want to see how is the material response to the gas sensor. Yeah, how it is behave.
Okay, all the best.
Thank you.
Right. Okay, I give all my colleagues last chance to ask. 3.
Dr. Hisham.
Oh yeah. Okay.
Amira here.
Yeah.
So Dr. Adilah, I just want to ask is about the performance. Is it how could you compare with the conventional one with your organic material compared to the semiconductor, the typical one that we have nowadays?
Yeah. So to be honest, right now we are still like long journey for the organic semiconductor material to beat the conventional material, obviously, because you know the conventional, the silicon has been like widely used in the market and also in the industry. So it is quite tough. And then in terms of the efficiency, for example, the solar cell, the efficiency is still not that at par with the conventional silicon. We have like put a lot of effort to improve the efficiency and also the stability, because in organic, for the organic semiconductor material, we do have a problem in which these material are easily degrade. So that is one thing in the problem of the organic semiconductor. But then we hope like one day, inshallah, we will be there as the OLED, you know, the OLED display in the market right now. So inshallah, one fine day we will be there, Dr. Amira.
Okay, right. Because I have seen a lot of futuristic technologies, which we just like use a very thin, like a transparent material, and make it like a phones or television on that. So it's kind of things that you can do. I mean, it's quite a good things, and inshallah, if maybe you can do that as
Yeah,
well.
inshallah.
It's
Yeah,
such a good thing to be done in the future.
yeah.
Yeah,
You're right.
okay, okay, good,
Mm,
Adilah. Thank you.
thank you.
You did mention something about the thing can be things like wearable devices, which is more friendly to probably to humans or something like that. Is that probably a kind of a good vantage point for organic semiconductor?
Sorry, I didn't get your question. Can you repeat?
You did mention something about the wearable devices and things like that.
Verbal.
Yeah, so meaning it has to be in contact with the skin and that. Well, usually organic material will be much better
Yeah,
received by no.
yeah, you're right. That is why recently, like researchers are trying to use the organic material in the fabrication of the flexible device, because the molecular structure you can see the material for phthalocyanine, it resembles to the molecular structure of the chlorophyll. So obviously it is like organic. We can say that it is organic and it is safe to human body. But yeah, as I mentioned just now, we have like a lot of work to do. We still have a lot of work to do, obviously, to like optimize things and all that.
Okay, last chance for a question. 3, 2, 1, 1.5. Okay, otherwise we thank Dr. Adilah again. So, okay, so I hope you have a enjoyable research program in the future. Okay, so thank you very much for participating in this seminar.
Right. Thank you all. Thank you for coming. Thank you for joining. All right. Okay.
Okay, I'm going to start the recording now.
So.
And right.